Okay, folks, we can get started. So my plan for today is I want to go through and clean up just a few odds and ends from the week 1 checkout. There are just a handful of things that I've noticed a bit of confusion about in lab. So I want to take some time to go back and add a little bit of clarification to a few concepts that were introduced last week. And then with whatever time, I don't expect that that'll take the whole lecture time. And with whatever time remains, I'd like to have another conversation about final projects, given that the Wednesday folks are going to be turning in their proposals on Wednesday afternoon. So it's coming up pretty quick. And given the proximity of the deadline, I thought perhaps it would be productive to have one more conversation about these projects that is a bit more specific than our last one. So the last time we talked about final projects, it was just sort of shotgunning ideas. And hopefully you all have had the opportunity to sort of mull over what you might find interesting, and maybe you have an idea for a final project, or maybe you just have an idea for a flavor of a final project that needs a little bit more work. So I thought it might be a good idea to, as a group, discuss people's ideas. And maybe that'll help folks that are having trouble coming up with ideas generate some of their own ideas and, add some specificity to vague notions, that kind of thing. But before doing that, there are just a handful of things that I wanted to clarify. The first thing that I wanted to just point people to is if we go to the write-up for Lab 3, I want to just remind you of a resource in this lab write-up that you may have overlooked, which is this recommendation for program organization. I've seen a handful of groups that are a bit confused about where precisely in their program various things should happen. Am I recording? Let me just make sure. Yeah. So for instance, I've seen some groups that are a little bit confused about where precisely are we supposed to be gathering the raw measurements, where are we supposed to be computing the complementary filter, these sorts of things. So I wanted to just take some time to walk through that. As with all of these labs, this is a recommendation, but this is a design class. So as long as you come up with a program that accomplishes the objectives as laid out, great, you can do whatever you want. But this is a gentle pointing in the right direction. One way that you might consider setting up your program is to have a single interrupt service routine that is connected to the PWM channel. Connected more specifically to the PWM slice, which has 2 output channels, right? So I'll just remind you that we are using these 2 PWM outputs to control an H-bridge. That H-bridge, that's another thing that I want to remind folks of. So we'll look at that in more detail in a moment. But the H-bridge has 2 control inputs in order to control the speed and direction of the motor. So we're generating 2 PWM outputs from the same PWM slice. That slice generates an interrupt flag to which we can attach an interrupt service routine. And the demo code that you all have been working with has that set up already. There's a PWM interrupt service routine attached to that particular interrupt flag. So one thing that you might consider doing is set up your program such that you have an interrupt service routine attached to your PWM slice, and then you have maybe 2 threads. And one of those threads could be doing all of the VGA graphics stuff. So in particular, it's going to be making a real-time plot of the output of the complementary filter, which is showing you the current position of the pendulum arm. And I would recommend scaling that such that you get that the output plot spans your full vertical resolution for that plot over the range of, plus minus a handful of degrees where you're actually controlling the pendulum, just so that you can actually see what's going on, as opposed to having it go between like plus 90 and minus 90 degrees where you get just little wiggles down here. It's kind of hard to debug anything like that. So scale appropriately in the vertical direction. So you'll have one of your threads that's doing all the VGA manipulation, and then you might have another thread that's taking user input. You're going to want to build an interface. You're asked to build an interface that allows for the user to change all of the PID controller gains dynamically. We haven't had a deep conversation about PID controllers yet. That's going to be next time. But in particular, you'll be asked to be able to change the proportional gain, the integrator gain, and the derivative gain from a command line, just so that you can debug and tune your controller quickly. Incidentally, that is the minimum required capability for your user interface. in order to debug, you might want to add more stuff to that user interface. You might want to change, oh, I don't know, the cutoff frequency of the low pass filter that you're using to display your controller outputs or something. Right? You might want to be able to make real-time modifications to the display in addition to the controller. We can talk about that, but I'm just reminding you that the hope here is that I am asking you to set up a certain amount of functionality, but I'm just reminding you that you are certainly free to add to that to the extent that it helps you to debug, and you might find that really useful to do. So your program, just in summary, it could look like a single interrupt service routine, which does most of the actual work in the program. So in particular, you enter this interrupt service routine. The first thing that will happen when you get in there is you clear the interrupt flag. That's in the demo code already, incidentally, but you clear the associated interrupt flag. You gather a batch of raw measurements. So in particular, a batch of raw accelerometer and gyroscope measurements, each of which has X, Y, and Z outputs. Right, so you gather a batch of raw measurements. You'll use those raw measurements as inputs to a complementary filter. I'm going to talk about this in some more detail today as well. But those are inputs to a complementary filter, the output of which is your estimate for the current position of the arm. You'll compare the current position of the arm to the desired position of the arm. The desired position of the arm, incidentally, is always straight up, right? So you'll look at the difference between where is the arm presently as compared to the vertical, and that's going to be your error, right? That's how far off we are from where we want to be. And that error ends up being the input to your PID controller. So your PID controller takes as an input the difference between where we are and where we want to be, and it uses that to compute a control output. The output, incidentally, of that controller is a duty cycle for your PWM channels that are controlling the motors. Right? So it'll output some number, probably a signed number, S-I-G-N-E-D, a signed number, that reports that dictates the direction and the speed that the motor should turn. And your graphical interface on the VGA screen will show you two things. On one of the plots, you'll have that complementary filter output so that you can see in real time where is the arm. And on the other plot, you'll have, again, in real time, the output of that PID controller. And that's one that you'll probably want to low pass. We'll talk about why and how in just a moment. But in order to just make the visualization easier, you're probably going to want to low pass the output of your PID controller just for visualization. You won't actually low pass the output to the motors, but just for visualizing, you might want to do that. That too, incidentally, in terms of things that you display, the minimum that I'm asking for you to display is the complementary filter output and the controller output, because those two pieces of information are really critical for debugging. You might want to add a few more things to help yourself debug or just out of interest. So in particular, I think it's really interesting on the plot that shows you the complementary filter output. Remember that the two inputs to the complementary filter are the angle as estimated directly from the accelerometer and the angle as estimated directly from the gyroscope. It's kind of interesting to also plot those so that you can see the accelerometer angle estimate, the gyro estimate, and the complementary estimate. And then as you play with your complementary filter weights, you can see how the complementary filter output moves relative to the accelerometer and gyroscope outputs. We'll look at that in more detail as well. You might consider doing that. Mahmoud had a good idea, which was on the controller output, wouldn't it be interesting to plot the proportional contribution to the controller, the integrator contribution to the controller, and the derivative contribution to the controller, in addition to the, the sum total of the three, which is the ultimate output of the controller, for debugging purposes. And then as you move this around, you can say, are my gains set such that, oh, I don't know, my proportional gain is just always overwhelming the other two contributions to the controller output, which that's valuable information to know, right? And it's just kind of, it would be interesting to watch as the thing balances, how do the weights shift among the three contributions to the PID controller? So you might consider adding that. You don't have to, but it would be interesting, and I think it would be helpful for debugging. Are there questions about that? And by the way, these two threads, they might go on the same core, they might go on different cores. You could set it up in either way, and I don't believe that there's a real distinct advantage to having dual cores here. That said, I believe that the demo code, if you just base it off the demo code, I believe that the demo code is set up such that one of the cores runs on core 0 and the other runs on core 1. So there's no real need to modify that if you don't want to, but there's not a huge advantage to the dual core aspect here. I had another good question in lab relevant to this program organization, which was the demo code is set up such that we are gathering the measurements, computing the complementary filter, doing the control calculation, all in an interrupt service routine that's attached to the PWM channel. And the question was, is there a reason that we're doing that as opposed to setting up a repeating timer callback function like we did in lab 1 that perhaps calls back at a kilohertz and gathering our measurements and doing all that stuff in that timer callback function? And you could do that, actually. So on some architectures, it may be the case that you would want to be careful about modifying the PWM duty cycle asynchronously from the PWM channel, because on some architectures, it may be the case that that introduces a glitch on the output for one cycle of the PWM channel. But remember from our conversation a few lectures ago that on the RP2040, those two registers that control the PWM channel's period and duty cycle, in particular the top register and the CC register, which stands for counter compare register, those are double buffered. So you could go in and modify those at any point in the PWM cycle's period, and the changes won't take effect until the next period starts. So you absolutely could set up a repeating timer callback function that runs at a kilohertz, and you could do all this control stuff in that. Why didn't I set up the demo code that way? Well, remember that from lab 1, way back when we were talking about timers and timer interrupts and stuff, one of the things that we spent quite a bit of time talking about was the levels of abstraction associated in particular with those timer callback functions. So you may recall that at the lowest level on that timer peripheral, there are those 4 alarm registers, and you can write a value to those alarm registers, and then when the value in that register matches the lower 32 bits of that incrementing microsecond timer, an associated low-level interrupt flag is thrown to which we can tie an interrupt service routine. And I mentioned that those repeating timer callback functions actually come not from a low-level hardware interface library in the CSDK, but actually from a high-level library that surrounds that low-level capability with a little bit more logic, so that just by using that low-level alarm hardware, it is implementing a repeating timer. But it's a slightly higher level of abstraction. And so for that reason, in lab 1, we did not see in the code an interrupt service routine tied to a low-level interrupt. This demo code is set up such that there is an interrupt service routine tied to one of those 26 interrupts that both cores see. In particular, it's one of the interrupts attached to the PWM hardware peripheral, just so that you see how that's done. Right? I just wanted to give you some demo code that showed how you tie an interrupt service routine to a lower level interrupt without the SDK levels of abstraction in between. So that if for your final project, you wanted to tie an interrupt service routine to one of the other available interrupts, there's something of a model here for how you would set that up. Right? So for instance, maybe you wanted to attach an interrupt service routine to an interrupt associated with one of the DMA channels, one of the low-level interrupts associated with a DMA channel. This is an approximate model for how you would do that for a different interrupt service routine. So that was my motivation for setting this up using the PWM interrupt as opposed to a repeating timer callback function. Any questions? Okay, I had a couple of other notes of things I just wanted to mention quickly. Oh, okay. I led some people down a path that could potentially lead to some hard-to-track bugs in a previous lecture, where I'll remind you, if we look at the demo code, and this is one of those things that maybe this manifests as a bug and maybe it doesn't, and it depends in part on how you have physically set up your circuit, stuff like that. But let me just remind you, let's go to the demo code. In lab 3, in the IMU demo, down in main, I'll just remind you that the IMU, the accelerometer gyroscope, is an I2C device. We're communicating with it over an I2C channel. And I'll remind you again that on an I2C channel, there are 2 lines. One's a clock line, one's a data line, and both have pull-up resistors attached to them. And the recommended starting point for those pull-up resistors is something on the order of like 4 to 5K. And what I said last time is, well, just turn on the pull-up resistors associated with these 2 GPIOs to which you have the I2C channels connected, and then you don't have to breadboard an external one. Okay, but the reason that this was sort of bad advice, actually, is if we go to the data sheet for the RP2040, and let's look in particular at the down. In particular, let's look at the electrical and mechanical appendix at the pin specifications. Let's scroll down just a little bit. What we'll find here in this table somewhere is the values of those pull-up and pull-down resistors. And what this table is reporting is that those resistances are in the range of 50 to 80 kiloohms, which is substantially higher than would be recommended for an I2C channel, right? So if you scope your I2C channel and you're using the pull-up resistors, what you might find is that the edges are a little bit soft, right? They aren't changing as quickly as you might want for them to be able to change. The reason that you would be seeing that is the internal pull-up resistors are too high than would be recommended for an I2C channel. So if you're having problems associated with noise, one of the ways that you might mitigate that problem, there are a few strategies, but one is stop using the pull-up resistors, which is as simple as commenting out these 2 lines, and instead breadboard an external pull-up resistor on each of the I2C lines that's 4 to 5K. And then I expect that you'll see much sharper transitions on your I2C lines. And by the way, scope the I2C lines, always. Always scope the I2C lines just to see what's going on. Any questions about that? Yeah.
I think the bus for I2Cs essentially look like a RT circuit, so that it has a capacitor in it, which causes this sort of rounded edges. And I wonder why you mean like when we have a high value bulk resistor that makes it softer.
It makes the higher pull-up resistors make it more difficult for the I/O pins to change the value of that voltage.
So say we have a bus that just rises like this. A higher resistance will cause it to smoother.
Yeah. Do you have a question?
Yeah, when we try to like kind of get the Pico to be connected with IMU, and it kind of like, I think it's not, because it's not stable connection, like it's sometimes it just like doesn't work, and when we try to reset Pico, and the program will get stuck in the MPU 6050 reset.
This one here.
Yeah, it just stuck there, and like we later found out that until we reset the MPU as well by cutting off the high voltage and then just like reconnected it again, and then reset like RP2040, like it will work this way. Like you have to reset both of them.
Okay.
And you have to reset MPU 6050 first.
Okay, that is good to know. So my expectation of what might be going on there is this MPU 6050 reset, there are I2C transactions that occur there. And if one of those fails, it blocks, right? So it just freezes the whole program. And probably what's happening is if you reset the Pico, the IMU remains powered, so it remains in this hung state. And so what you discovered is you have to actually remove power from the IMU and then power it again to get it out of that hung state, and then things worked more reliably?
Yeah.
Okay, okay. That's really good to know. Any other questions or bugs from any folks? Okay. The other thing I wanted to show you is the data sheet for the motor driver that we're using. Just remind you that this is an H-bridge motor driver, and it has two control inputs. Let me remind you what an H-bridge is. There are a few different flavors of this. So this is an example of one that uses both NPN and PNP resistors. There are other versions of this that might use all NPN resistors. But in short, I'll just remind you that if you're controlling an H-bridge, generally what you're doing is controlling this pair of transistors and this pair of transistors separately. And the notion is that if we turn off this pair of transistors and turn on this pair of transistors, then we can get current to flow through this direction, in this direction through the load, the motor in this case. If alternatively we turn off those two transistors and turn on the other two, we get current to flow in the opposite direction through the load. So what we're doing in this class and in your program is one of the two, so your two PWM outputs are controlling one or the other pairs together. And so say you want for the motor to turn, in this direction at some speed, you would do that by making the duty cycle to the PWM channel that controls these two transistors 0, just to say you turn those off. And then you pulse width modulate these two transistors in order to control the speed of the motor in this direction. And then likewise, if you want to go the other direction, you would turn these two off and pulse width modulate the other two transistors to control it at some speed in the other direction. And then, of course, if you set them all to low, you stop the motor. You can build these yourself, and in some of your previous classes, perhaps you've built H-bridges to control things like little robots that run around on the floor. If you build this yourself and you turn on all the transistors, what happens? Yeah, funny smells start coming out of the breadboard. Things get really hot. You have to replace transistors. Nothing good, right? On this particular integrated circuit, the thing that I just wanted to point out is there is, if we scroll down here in the data sheet, a logic table here that shows this is input A, input B, output A, output B. It's showing us for each of the possible control inputs to the two, for each of the possible inputs to the two control channels, what are the outputs? And some of this stands to reason. So input A is high and input B is low. Output A is high and output B is low, which is to say the motor's turning in one of the directions. If we swap which of the inputs is low and high, the outputs also swap. The motor turns in the opposite direction. If both the inputs are low, clearly it's the case that the motor doesn't turn, but the outputs are low. This integrated circuit will protect you from yourself. If on this integrated circuit you make both the inputs high, the consequence is the motor just breaks. The output's low. I'm pointing this out because this can introduce a bug where suppose you're testing the PWM output, the two PWM output channels, and just to test things, you have very reasonably said, I'm just going to set both the PWMs to the same duty cycle, same waveform. If you do that, so you have two PWM outputs that look identical, and they're going into input A and input B of this motor driver, then both the inputs are always either going to be high together or low together, and the motor won't move. And that is the expected behavior for this integrated circuit. But you could be sitting there with the scope, looking at the waveforms on the scope, and saying, why isn't the motor turning? It's because you're driving the two inputs together, right? If instead you were to ground one of the inputs and pulse width modulate the first one, the expectation is that the motor turns at some speed in one direction. And then if you were to ground that one and pulse width modulate the other one, the expectation is that the motor turns at some speed in the other direction. Right? So just something to look out for. Any motor driver questions? Yeah.
For the capacitor that we put between OA and OB on our circuit, does this motor driver driver not have one built in?
It does not, it has built-in snubber diodes. So remember when we were talking about the DC motor circuits, the recommended circuit included a diode that pointed from what was usually the low side of the motor back to the high side of the motor. And this is because if we're pulse width modulating the motor on and off, the inductive element in that motor will produce very large voltage spikes of opposite polarity. And so we have this snubber diode here in essentially all motor driver circuits to allow a safe loop through which that reverse polarity can travel without destroying anything else. This integrated circuit does have inbuilt snubber diodes. It does not, to my knowledge, based on my reading of this stuff, it does not have an inbuilt bypass capacitor. So that one you breadboard externally. Yeah. And that one too, I'll remind you that I would recommend putting that capacitor directly across the motor as opposed to across the power supply. Okay. Any other questions? Okay, interrupt me if anything occurs to folks. The next thing I just wanted to take a quick look at, just to clarify a bit further, is the complementary filter. This is not complicated. There's just a few steps that perhaps we should talk about a little bit. So let me just remind you, there is accelerometer information going into the complementary filter, and there's gyroscope information going into the complementary filter. Let's first talk about what we're doing with the accelerometer, then we'll talk about the gyro. So this is a picture of, it's a schematic picture of what your pendulum arm looks like. So here's the arm. There would be a wheel up here, and we have the accelerometer and gyro rigidly attached to the arm so that as this tilts and turns, we're using the accelerometer to measure the direction to the center of the Earth. It's measuring gravity. In particular, if we have it oriented in this way, then we would be, as this tilts the y output of the accelerometer would be telling us the magnitude of gravity in this direction, and the x output of the accelerometer would be telling us the magnitude of gravity in this direction. What we're interested in, incidentally, is this angle, right? So you can deploy some trig, and you know that this angle theta is given by the arctangent of ax over ay. No mysteries there. What we're doing in this lab and in the demo code is cheating a little bit because we're recognizing that that arctan function is expensive. And so we're going to make a simplifying assumption that we are only care to control this motor over a small range of angles. So we'll apply a small angle approximation here, right? We're just going to approximate arctangent by the first term of its Taylor expansion. So we'll say, yeah, that this angle is exactly equal to the arctangent of ax over ay, but that's pretty darn close to just ax over ay. Yeah.
What if I ruin the small angle approximation by just like tapping it?
If you tap it quite far out here, then it's a bad approximation. But you will not be able to recover. If you tap this outside of where the small angle approximation holds, the speed and the mass of the reaction wheel that we're using, you're not going to be able to catch it. You can only really catch and control these things within a range of angles where the small angle approximation is reasonable.
This seems about as effective as just tightening the screw on the pendulum, so it doesn't.
So that's an interesting point, right? So there is this observation that, we're holding this whole assembly to its Lego base with a little screw. Gosh, we just tighten a little bit. Maybe it becomes a little bit easier to hold. And in the limit, I agree with you. If you just yank that thing down so that it literally can't move, then yeah, the thing is going to stay balanced because it's not ever going to fall over. But I think what you'll find is if you try to cheat this a little bit and add yourself just a little bit more friction, it becomes harder to control. Because you come off a little bit, and it's more difficult for the wheel to kick you back up and fight against that friction. And so my experimentation shows that you have more of a tendency just to fall over. So it is easier with less friction. Unless there's so much friction that it doesn't move, right? But that's a boring control problem. What's that?
Works.
How tight was it? Okay. Okay, so this is one of the inputs to the complementary filter is our estimate for the tilt angle as measured just from the outputs of the accelerometer. And as I've mentioned, this is nice in the sense that the error in our calculation of that angle tends to be unbiased, which is to say, if you have true knowledge of the actual angle and you're plotting the angle as estimated by the accelerometer against that true angle, it bounces around the true angle. It doesn't have a bias, but it has a lot of noise. So much noise that we couldn't just use this as the input to our PID controller and have the controller work. It's simply too noisy, especially once the motor starts turning. The noise explodes. So we add a little bit more information, and in particular, we add a second estimate for that tilt angle that comes directly from the gyroscope. So what we do is we say, all right, the pendulum is going to start at some angle. Maybe it starts, we're holding it straight up when we start. And then each time into this interrupt, I'm going to gather a gyroscope measurement. In particular, I care about one axis of that gyroscope measurement. If this is the z-axis, we care about GZ, rotation rate in this direction. And we say, well, I am just going to integrate the output of my gyroscope to maintain an estimate of my current angle. I know where I started. I know the angle that I started. So in the next time step, I'm going to say my new angle is about equal to my old angle plus the output of the gyroscope, which is in units of something like radians per second, right? It's rate of change of angle, times delta time. So it's an Euler approximation. So we just pop ourselves to the new angle. So this is giving us a second estimate for our angle. This has its own set of problems, right? And its own set of things that are nice. What's nice about this is the output of the gyroscope is far less noisy than the output of the accelerometer. If you plot this output of the gyroscope, it looks much smoother than the output of the accelerometer. Did I say that right? If you plot this output of the gyroscope, it looks much smoother than the output of the accelerometer. However, it develops a bias. So if you were to plot this angle against some, true angle, if you knew the true angle of the pendulum, what you would see is, you do little wiggles, and those little wiggles are represented in the output of your gyro estimate, but your gyro estimate wanders away from the true angle, develops a bias. So the complementary filter, it's a simple algorithm that allows for us to maintain the short-term accuracy of the gyroscope, the less noisiness of the gyroscope, and the unbiased nature of the accelerometer. So in particular, what we do is we enter the interrupt service routine. We gather a batch of accelerometer and gyroscope measurements. Let me make that a little bigger. That didn't really help. That's okay. We gather a batch of accelerometer and gyroscope measurements. We use that batch of raw accelerometer measurements in order to compute our accelerometer estimate for the angle. And we do so by taking AX over AY, that's our first order approximation of the arc tangent, multiplied by a constant that converts this from radians to degrees. Just, we wouldn't have to do that, but okay. It's just, I wanted it in degrees. So we compute our accelerometer angle. Likewise, we gather a gyroscope measurement. We gather all three, but the only one that we actually care about is GZ, right? Rotation in this direction. We multiply that by our time step, delta t, which in your case is going to be 0.001, right? Because we're running this at a kilohertz. So it's going to be the fixed point representation of 0.001. You multiply it by the time step. This is that the output of this gives you a gyro angle delta, which is to say, how many degrees have we moved since the last time we did this, since our last interrupt. We add that delta to our previous estimate for the pendulum position to give ourselves the gyro's angle estimate. So now we have the accelerometer estimate for the angle, we have the gyro estimate for the angle. The complementary filter then is just a weighted average of the two, where the weight for the gyro is substantially higher than the weight for the accelerometer. The gyro weight might be something like 0.99. The accelerometer weight might be something like 0.01. Incidentally, weighting the gyro so high and the accelerometer so low is the same as high passing the gyro and low passing the accelerometer. Okay, so we're high passing the gyro, we're low passing the accelerometer to generate, and adding the two, of course, to generate an estimate for the angle that includes information from both the accelerometer and the gyroscope. And that estimate is better than we could get from the accelerometer alone or from the gyro alone. We're combining information from the two sensors in order to get a better estimate. So one question, you look at this and you say, okay, I understand how this works sort of once the system's running. It perhaps stands to reason that this needs to be initialized, right? So for the first time you go into the interrupt, this needs to have some value, right, that you can actually start this process. You could do this in a bunch of different ways. One way is you could say, you know, I am going to assume the user always starts the program holding the pendulum up. That's a reasonable assumption. I'm fine with that. Alternatively, in main, before you start this whole process, you could gather a batch of measurements and initialize the complementary angle to whatever you calculate just from the accelerometer, right? Just to get yourself in the right ballpark to start, and then it'll go through and correct itself, right? Yeah, either would work. Yeah.
But when you calculate in gyroscope measurement, are you already assuming the user is kind of holding the pendulum up?
Not necessarily. You certainly could. So if you initialize this complementary angle to 0 degrees or 90 degrees or whatever convention you choose to represent straight up, then yes. If instead you initialize it to whatever you calculate from a single batch of accelerometer measurements, maybe you start it up and the system's leaning on its side, then you would initialize this whole filter to an angle where the thing is leaning on its side.
I just thought the gyroscope is going to assume the initial position is going to be up so that it calculates the difference between that and the current measurement.
So what we need is an initial theta naught, right?
Yeah.
That theta naught might be 0 degrees, 90 degrees, whatever it is that represents straight up, if you're assuming that the user is starting this thing holding it straight up. Or alternatively, you might gather a batch of accelerometer measurements, compute an angle, and then before you start this whole process, you say theta naught equals whatever angle I computed from the accelerometer.
Let's expect like the noise.
It is, yeah. So it's not going to, it's just to get you in the ballpark, right? And then because you are starting this process where you're high passing the gyro, low passing the accelerometer, it corrects itself and you end up with complementary filter outputs that are better than you could get from either the accelerometer or the gyro. And there's some code down here to help you. So, you know, this would be sort of the first part of your interrupt service routine. You clear the interrupt flag, that's not represented here. Gather a batch of measurements, compute the accelerometer angle, compute the gyro angle delta, and then use those two to compute the complementary filter output. Okay. Last thing I just wanted to add some clarity to is it is not of particular relevance for last week's checkout because last week you were just specifying a duty cycle through a command line to say motor spin this way, motor spin that way. Ultimately, those duty cycles are going to be computed by your PID controller, and they might be noisy enough that it would make visualization difficult. So my recommendation is that for visualization only, you low pass the output of your PID controller before you put it onto the VGA screen. And the particular low pass filter that you might consider implementing is something like this, where you say, perhaps PWM on time is the output of your PID controller, right? So this is what your PID controller produces from interrupt to interrupt to interrupt. And you could say, the value that I will display on the oscilloscope we'll call it motor display, is going to be equal to the previous value that I displayed plus the new on time, the new duty cycle as computed by my PID controller minus my previous value for the PWM duty, my low pass PWM duty cycle, right shifted by some amount. It's a digital low pass filter, and it's slightly esoteric looking. You can arrive exactly at this line of code from, hopefully we can all agree that this is a low pass filter, right? So if we start from the low pass filter that is our old friend and consider the voltages and currents through each of these elements, we can, I won't go through this process here in lecture because I don't think it's really necessary, but you can read through this. What you end up with is an equation for an output voltage that maps directly to the line of code that we just looked at. So this is an explanation of why that line of code is low passing that value PWM on time. And it's explaining it by deriving the equation from an RC low pass filter, which is hopefully a familiar low pass filter that we all kind of understand. So incidentally, this low passing stuff, this would not be taking place in the interrupt service routine probably. This would probably be taking place in the thread that's responsible for VGA drawing. You might signal that thread from the interrupt service routine. Maybe the thread waits on a semaphore, and the interrupt service routine signals it and says, oh, here's some new stuff to draw. You're probably doing this computation in the thread. Okay. We have like 10 minutes remaining. What are people thinking for final projects? Does anyone want to share? Does anyone have a vague notion of a flavor of project that they would like to do and they're still working on the specifics? Yeah?
We kind of want to working on a ray tracing program on Pico. And I was thinking about, is it possible to have that much color choices on the VGA screen, or we should have our own screen?
I think a ray tracing project would be really interesting. If you want more colors, you can, with really quite minor changes to the VGA driver, get yourself 4-bit color as opposed to 3-bit color. And that gives you a nice gradient, which might look nice for a ray tracing project. There's some example, we can talk about that in lab, but yeah, I think that would be a nice thing to add to the VGA driver for something like this. Do you imagine sort of, in my mind, the canonical example for ray tracing is like a reflective sphere above a checkerboard?
Like a Cornell box.
Yeah, okay,
Something like that.
okay.
But like,
I think if you drop the
not too plain, just like load a model and just plug into the VGA screen with a display. I was thinking about maybe you could like add more features. For example, we have like a main menu so they can choose between different models to render.
Sure. I think that's a good idea. And this, incidentally, it reminds me of, as you start thinking through your final projects, one of the things you just reminded me of is a nice characteristic of a final project proposal is one that has a series of milestones where at each of those milestones, you have something demoable, right? Because it is often the case that we start working on these things and something that you or I or both of us thought would be relatively simple is much more complicated than we thought. Happens all the time. So having a set of milestones that leads you to some ultimate objective is a good idea, so that if we encounter something that's more challenging than we imagined, then, you know, there's some reasonable place slightly before the ultimate objective where there's also an interesting demo. And likewise, by the way, it's nice to include some reach goals as well, because sometimes the opposite occurs, where we think some problem is going to be tremendously difficult, and then you work on it for a few days and you go, oh, actually, we got this together much more quickly than we thought. So it's nice to include some stretch objectives so that you can extend the project to the extent that you are able in the weeks that you have. Okay. Is anybody thinking robotics things? Yeah?
I kind of wanted to make a boat. I didn't consult with anyone about that. I just had that idea when I was walking through Dublin.
Okay, okay. A boat.
That's the entire idea about this.
Okay, okay. A boat would be, I don't think, I have never seen anyone make a boat in this class. That'd be pretty interesting. We'd have to talk about how exactly testing is going to take place. But well, we could figure something out.
I'm sure there's a bathtub somewhere.
We'll figure something out, okay.
All right.
By the way, I will post I will set up a Google form through which you can submit order requests. So if anyone here is interested in roboticsy things or is interested in any project that requires some extra stuff that you would like to buy, up to a threshold that I'll double check, but I think it's like $20 or $25, you can just request that stuff and I will purchase it. So I'll set up that Google form, and I'm getting your proposals this week. So I will say, let's see, I want to have a couple days to look over the proposals. So I will put on Canvas sort of the date at which I will make the first round of orders. So I'll ask for everyone to have their orders submitted by that date, and then I'll make the first round of orders. And then I'll probably do one more subsequent round for all the folks that go, oh my God, we forgot to order, whatever it is. So there will be at least 2 rounds of ordering up to some threshold. You may go above that $25 cap up to $100 or $125, but above about $25, it's on you guys. And like I said, no more than $100 to $125, right? Yeah.
So I have another idea. So you like make an online gaming device.
An online gaming device.
You know, you can use a Pico tablet to do some programming.
Sure. Yeah. Yeah. I'll mention again too. The demo just reminded me again. If anybody wants to order some Pico Ws, if you want for your project to have internet connectivity, you're very welcome to do so. There's a supply of those, so we can order those as well. Yeah.
What are like Cornell's rules about like setting up a server?
What are Cornell's rules about setting up a server? That's something we'll clarify that with CIT. So yeah, if you're doing an internet connected project, that's totally fine. But because that flavor of project is relatively new to this class, I'll meet with CIT and just make sure that we're doing it in a way that they're all happy with. Yeah.
Not like a Pico W for own use, maybe like
No, I will only buy things for your final projects. But that said, it's like $6, right? So cost of a cappuccino. All right, other thoughts? What are other people thinking?
What's your other part?
Yeah. Per group. That's a good question. The budget is 25 per group. Anybody thinking video game?
Not video game. What's the limit? 125 or like $25?
I will double check it, but it's on that order of magnitude, 100 to 125-ish bucks.
Okay.
Yeah, yeah.
It's 125.
He's saying I can't spend $1,000 to get the project done for me.
Okay.
Because then he'll just say that. That's what he
Anybody doing an audio project? Anybody thinking on? Yeah. What are you guys thinking?
we're thinking of just making like the audio synthesizer with like the requisite knobs to change. So it'd be like going back to lab 1, but with 2 separate oscillators, maybe like a low frequency oscillator to kind of add on top of that.
Okay.
But it would mostly just be playing around with changing.
That sounds great. Yeah, so audio projects demo really nicely, right? They're fun to play with. They're fun to demo. Yeah.
I was thinking about doing something where it's like you play an instrument and you try to figure out what instrument it is. Part of that is the implement. Like the timbre.
So am I correct that the project is one sort of, you're doing some sort of frequency analysis on audio input to classify what this thing is based on something like frequency content? I think that's challenging but doable, and maybe is kind of nice in the sense that you could start with classifying between this or that, and then depending how far you get with that, you could add more and more things that you're trying to classify. Another fun classification problem might be bird songs. Particularly songbirds. Songbirds are kind of nice from a frequency analysis perspective because they're generally only singing one frequency. They modulate the frequency, but for a songbird, there aren't a lot of overtones. There aren't a lot of harmonics. It's usually just one frequency. So perhaps that makes classification a little bit easier. You could start with saying, like, I'm going to just classify northern cardinals versus orioles, or something like that, and try to add more. Any other audio projects people are thinking? Anyone thinking head-related transfer function? Thinking about that maybe? The head-related transfer functions, I'll just remind you, these are projects where you synthesize slightly different sounds into different earbuds in order to make it seem like sound is coming from some spatial direction. Those are fun projects. They demo really nicely. Okay, we're out of time. Oh, one more? Yeah. So yes, a final project that is based on extending one of the labs is perfectly within the realm of possibility. It just has to be extended to a far enough extent that it, makes sense as a 4 to 5 week final project. But totally fair game.